Hi, my name is Guy Vine and I've come to speak to you about the prime twins. Not the primes, but the prime twins. What is the definition of a prime twin? Well, it's quite simple. It's two prime numbers as close together as they can be, like 29 and 31. They can't be any closer because the number in between is not a prime, it's an even number. So that's a prime twin. Now, we know that the primes themselves go on forever and ever. They never stop. There's no last prime. But what about the twins? Do the twins go on? Or is there a last prime twin? There are some very large prime twins, well over 10,000 digits long, but they're thinning out. Do they thin out so much that in the end they dry up altogether and stop? Or do they continue forever? Well, it's an unsolved problem of mathematics, and this little video clip aims to give you the proof of it one way or the other. So let's just have a look and see what's involved. We'll start at the beginning. What is a prime twin? Well, it's a pair of primes separated by one even number. For example, 5, 7, 11, 13, 17, 19, 101, 103, and so on. The next question is, do the prime twins go on forever? Or is there a last one, beyond which there are no more? Well, this question has never been answered, but this paper that we're looking at now is aims to give an answer. Where shall we begin? Well, all the twins, prime and composite, which are less than or equal to x, are 1, 3, 2, 4, 3, 5, and so on, up to x minus 2 and x. Clearly there are x minus 2 of them. Now the question we've got to ask is this: how many of them are prime? Now, as we ponder these twins, 1, 3, 2, 4, 3, 5, and so on, we can see that a half of them are composite to 2. Take the first two, for example, 1, 3, and 2, 4. Half of them, namely the second one, 2, 4, is divisible by 2. And that means that a half of them are prime to 2, not divisible by 2. That's what the 1, 3 is. 1 and 3, neither are divisible by 2. If we then take a set of 3 twins, you'll see that 2/3 of them are divisible by 3, and therefore 1/3 of them will be prime to 3. Again, take 5, the first 5, or any group of 5 twins, and you will see that 2/5 of them are composite to 5, and therefore 3/5 are prime to 5. If we take the general case, PM, 2/pmths of them are composite to PM, and therefore 1 minus 2 over PM of them are prime to PM. Now, if we want to obtain the proportion of these x minus 2 twins prime to each of those primes, 2, 3, 5, all the way up to PM, then we multiply the fractions together, and hence the approximate number of twins prime to 2, 3, 5 up to PM is n equals x minus 2, that's the number of twins, times the proportion prime to 2, a half, proportion prime to 3, a third, proportion prime to 5, that's 3/5, proportion prime to 7, that is 5/7, and so on, right the way up to the last one, which is 1 minus 2 over PM. That product may be expressed as in the lower, the last line, n equals x minus 2 over 2 times the product of 1 minus 2 over pj, where j runs from 3 to m. Now, to ensure that the twins less than or equal to x and prime to bm, bm is a group of primes 2 up to pm, to ensure that they are also prime, we require that x lies between pm squared and pm plus 1 squared. Now a prime twin, p minus 2p, prime to bm, can't belong to bm, and so p must be greater than pm plus 1. Also, since the twin p minus 2p is less than or equal to x, where x is less than pm plus 1 squared, therefore p is less than pm plus 1 squared. And so, putting those two things together, p lies between pm plus 1 and pm plus 1 squared. Putting together now where we've got to, n equals x minus 2 over 2 times that product. We'll count the number of prime twins between pm plus 1 and pm plus 1 squared. The product is an approximation, but a good one. But at any rate, it's counting prime twins between those two values. Let's consider what happens in the two cases. Either the prime twins stop or they go on forever. If the prime twins stop and the last prime twin is pz minus 2 pz, then for all m greater than or equal to z, all prime twins will be in bm. They will lie somewhere in that set of primes 2, 3, 5 up to pm. And so there will be no prime twins between pm plus 1 and pm plus 1 squared. On the other hand, if the prime twins persist, go on forever, then as m tends to infinity, so the number of prime twins between pm plus 1 and pm plus 1 squared also tends to infinity. Confronted between two choices. As m tends to infinity, so the number of prime twins between pm plus 1 and pm plus 1 squared is either 0 if the twins stop, or it tends to infinity if the twins persist. We must choose between 0 or infinity. Shouldn't be too difficult. Well, what does our approximation say? N equals x minus 2 times the product, the proportion of those x minus 2 twins which are prime. What does that approximation say as m tends to infinity? Does it say 0 or does it say infinity? Well, we may easily show that as m tends to infinity, so n tends to infinity. N being the number of primes between pm plus 1 and pm plus 1 squared. We have n going to infinity, and yet in truth having no prime twins at all between pm plus 1 and pm plus 1 squared. We can't have the approximation saying infinity, but the truth being 0. So that settles it. The prime twins persist. There is no last prime twin. Well, there we are. That's my proof for the persistence of the prime twins. They persist to infinity. It hinges on an approximation for the number of prime twins below x tending to infinity, and choosing between that, or if the truth is that they stop, the prime twins stop, then the number that we're trying to approximate is actually 0. And the whole thing hinges on the fact that we can't have an approximation saying it goes to infinity whereas the truth is 0. I leave those thoughts with you. Thank you.